Hello, my name is Josh Zdarsky. I'm a physics student working in the Renewable Energy and Environmental Research Laboratory here at Hamline. What we would like to demonstrate for you today is our procedure for the fabrication of lithium-ion batteries and supercapacitors. Now, what we produce, the devices we produce, are pretty much kind of same recipe, different ingredients, but we can talk about some of the differences right here, where with batteries, we're having the slow release of charge, aiming for longevity. We want this to have as much energy in it as possible to last as long as it can. And that charge is mainly stored via electrochemical processes. Whereas with the capacitor, we're getting rapid discharge, kind of like when you're accelerating your Tesla and you want that little kick. That kick and speed comes from that capacitor then. And that charge can be stored both electrochemically and via the process of induction. It's important for us to improve these devices because as the production of energy from renewables ramps up, the issue then becomes, how are we going to store this energy? So our work then is to improve how much energy that can be stored in these devices and how efficient that they handle the charge and the discharge of energy.
Here I will show off the ingredients for the slurry, where we have a lithium compound containing nickel, cobalt, and magnesium, or NCM, which is used for the cathode. We also then have carbon black, which is another component of the slurry. And then we also have graphite powder for the anode. We then also have a binder solution containing polyvinylidene fluoride powder, or PVDF, dissolved in 1-methyl-2-pyrrolidinone, or NMP. Current research suggests that these materials should be combined in a ratio of 80% active material, the NCM or the graphite, 10% carbon black, and 10% PVDF. As a little trick, I've folded the white paper diagonally twice so as to make it easy to transfer the powders then from the white paper into the mortar. To start out, I'll be weighing 80 milligrams of the active material for the nickel, cobalt, magnesium powder to create the cathode slurry. It's typically easier to start adding in a little bit at a time because it'll be easier then to put just a little bit more on rather than having to take more off. Having finished weighing the material, I'll be shutting the balance and allowing the air currents to come to a stop so that we can take the measurement. We would also like to keep track of these numbers so that we can use them in our calculations for capacity and efficiency later down the line. Or when it comes to capacitors, we would then be able to use it to calculate the specific capacitance per gram of active material. Having taken note of the number, we're now ready to transfer that powder from the white paper into the mortar. Once again, I'm using this trick to fold the white paper diagonally twice in order to make it easier to hold and transfer the powders from the balance into the mortar. Another thing that's important as we go along here is to make sure that between uses in different powders that we are cleaning our scoops and our instruments as we go along in order to avoid cross-contamination and incorrect numbers when it comes to calculating certain things. Moving on to weighing out the carbon black, I'd like to note that another reason why you want to put in only a little bit at a time is because the densities of the powders do vary. So what appears to be 80 milligrams of the powder for the nickel, cobalt, magnesium might be, let's say 10 milligrams for the PVDF, or for then the carbon black. So for this reason, you just want to be careful about how much powder you're adding in at a time, and try and start with a little bit until you sort of get a feel for how much is an appropriate amount. Once again, now that the powder has been finished weighing, and once we've taken note of the number, we are transferring carefully the powder from the balance to the mortar. Bring that over. The weigh paper, along with any other items that are coming into contact with the powder, will be discarded in hazardous waste due to the slight toxicity of the powders. But what we have here now are the two powders mixed together and ready to be ground. But again, an important thing is we want to clean as we go. So we are taking then a Kim wipe and soaking it with ethanol. And similar to how we cleaned the scoop, we're going to turn off the balance and clean it gently in order to make sure that we have a clean lab and a safe workspace. Having transferred the powder from the table into the fume hood, you will then begin grinding the two powders together. Here I'm pointing out that the color of the powders is not quite the same, and what I'm getting at there is that it's important for these powders to be uniform. When we get to the slurry deposition, we want to have a thin, homogeneous film. If we don't get that thin, homogeneous film, then the properties of our device are not going to be as good. So, having started with little circular motions with the pestle, I'm also using the scoop to gather the powders together as much as I can. This grinding will be done for 20 to 30 minutes. And some powders will be lost, so we will try to weigh out our material after grinding to see exactly how much that is. For this reason then, it's better to be a little bit over the target mass than under it for an ideal material ratio. Now that the grinding has been complete, we're ready to extract our powders and place them in a vial. For smaller recipes, a 5 milliliter vial works well, but for larger recipes, a 20 milliliter vial tends to work better. We'll reach a point where we've extracted so much that it then becomes difficult to get it out with the scoop. So now we're going to come back and use the weigh paper again, where we're going to fold it diagonal twice, and we're going to then pour what's remaining of the powder onto this weigh paper so that we can try and transfer it into our vial. Get as much of the material out as we can. I think we've been doing a good job. There's not a whole lot of stuff left there. Transferring the material over the mortar then is ideal, because in case anything drops, it will be caught by the mortar, and you can pick it up and try again. Allow that to fall in. And As previously mentioned, we were going to try and weigh our material afterwards to see how much that we would have lost. With 10 milligrams of carbon black and 80 milligrams of active material, ideally there should be around 90 milligrams of material left over. So before we add that binder solution, we're going to weigh that out. But first, since we've taired it, we'll now be able to add our material and see just how much is in there. Here, we're noticing that the amount of material that we have is less than what we should ideally have. So we're taking note of that number, and we can make then some other considerations in the future as we attempt to attain that idealized material ratio. We are now ready to add the binder solution, which contains 5% PVDF powder by mass. Because of this, we will need to add enough binder solution so that the 5% of it totals at the desired 10 milligrams of PVDF powder. We will need to add 200 milligrams of binder solution in order to get a total of 10 milligrams of PVDF. With this dropper bottle, this will come in between 6 to 8 drops. For the binder solution, it may be better to be under the target mass rather than over, since the other powders are already likely lower than the target. In this way, we can attempt to keep them more equalized. We will also want to keep track of this number as well, and then calculate 5% of that for the PVDF. After adding the solution, we may notice that it isn't quite homogeneous as we desire. We may then want to mix it over a vortex for the powder to soak in the solution, or we might add more solvent without PVDF so that we obtain the slightly runny consistency that is ideal for slurry depositions. I briefly ran it over a vortex, and you can see that we have just a slightly runny consistency. Again, that is what will be ideal for our slurry depositions. We then add a small magnetic stir bar into our vial so that it may be further mixed and homogenized. The hot plates are equipped with both heat elements and magnetic stirring, the latter of which can be controlled with the knob on the right. Setting our slurry onto the hot plate and turning on the magnetic stirring, we will allow this to sit and stir for 10 minutes before moving on to the next step. After allowing it to stir for 10 minutes, we will transfer the vial into a sonicator. This device helps to mix solutions by using sound waves propagated through water in the container to cause physical vibrations and disruptions in our slurry. This speeds up the dissolution of powders into the binder solution. We will do this 3 times at 20 minutes for a total of 1 hour of sonication. Because of the heat that can sometimes arise from sonication, the slurry may become thicker. If this happens, we will then have to add more NMP so that we maintain the desired consistency post-sonication. For the sake of repeatability, we will want to take note of how much NMP is added both before and after sonication. This can be very helpful as you try to consistently recreate a particular recipe. I tend to add 2 drops of NMP at a time, then mixing briefly to see if the consistency is desirable. Adding drops until that consistency is obtained, we will take note of how many drops and how much mass is added, and then place our vial back on the hot plate to be stirred for 1 hour. In order to deposit the slurry, we will use a sheet of glass and a piece of aluminum foil cut into a strip. I will start by applying a copious amount of ethanol to the glass sheet and spreading it around with a Kim wipe. I should note then that the aluminum foil is what will be used for the cathode, whereas copper will be used for the anode. We want to cast on the dull side of the foil, so we will place the foil over the ethanol with the shiny side down. Having the ethanol underneath the foil allows it to almost stick. With another Kim wipe, we can smooth out the foil, which we do so that the slurry is deposited evenly over the entire surface. Now I'm wiping off the excess ethanol on either side of the foil so that I can place tape down, creating a thin strip to deposit the slurry. The thickness of the deposited slurry can be varied by adding more layers of tape. Ideally, the tape should be longer than the strip on either side. The size of the strip should depend on the amount of slurry made. More recipes should either be longer, wider, or perhaps both. The size of the strip for single recipes should be long, but relatively thinner. With the foil smoothed out and secured, we are ready to deposit the slurry. We will take our clean scoop and start by trying to pour out as much slurry as we can. We want to do this in a bar along the top of the foil. It doesn't need to touch the tape, and is actually better if you keep the material further from the edges. We can use the scoop to remove the stir bar. Since it also has slurry on it, I will roll it around, trying to get the excess off before I remove it and clean it. Be very, very careful with the stir bars and keep close track of where you put them. They are quite easily lost. We will then continue to scoop out slurry. Gently dab the scoop along the surface as you add more of it. Again, it's better to have the slurry further from the edges and as densely packed in the strip as it can be. Once you've removed as much as you can, you're going to use a glass rod to spread out the material. We're going to clean the rod with an ethanol-soaked Kim wipe so as to remove any rough particles on its surface. Then, holding the rod with the tips of your fingers like so, and your palm well above the rod with elbows raised, you will slowly pull the rod towards you in a smooth and continuous motion, with your fingertips gently pressing the rod into the tape as you pull. This should be done no more than twice, and ideally is done only once. The glass rod will then be cleaned with another ethanol-soaked Kim wipe. We now need to transfer the casted foil from the glass sheet to the hot plate. We will do this by using the edge of a razor blade to cut along the tape on both sides and remove the sheet gently. Ideally, the sheet should be kept as flat as possible so the slurry doesn't pool in other areas and remains evenly distributed throughout the piece of foil. Here, I am turning on the hot plate to 80 degrees Celsius and then transferring the foil, taking care to keep it as flat as possible. it would be better to place the foil on the hot plate before turning the knob to the desired temperature. If we shock the slurry with heat right away, the evaporation of the NMP solvent will occur too quickly and leave the material cracked and uneven. We will leave the casted foil on the hot plate until we see that all or most of the NMP has evaporated, at which point we will transfer the foil from the hot plate to the vacuum oven. Taking our casted electrode and placing it into the vacuum oven, we will begin the process of dropping the pressure. Here, I'm plugging in the pump behind the oven, which begins to evacuate the chamber. I then check the vent valve to ensure it's closed, and then open the valve between the oven and the pump. The needle in the gauge will need to drop below a black dot before closing the valve and turning the pump off. This will take about 10 minutes to occur. Here, I will close the valve and unplug the pump. The oven is preset to bake at 80 degrees Celsius for 600 minutes, or 10 hours. This will allow all solvent to evaporate and leave behind only the desired materials, and the vacuum will ensure a clean environment free of other particulate. With the flip of a switch, the oven is on, and we let it set for 10 hours. After the 10 hours have elapsed, we will turn off the oven and vent the chamber. It's important to vent slowly, otherwise the rapid change in pressure will cause your foil to fly around and may result in damage or reduction in quality. Once the oven is at atmospheric pressure again, we will close the vent valve and remove our casted foil from the oven. For some devices, they may roll up their electrodes into a tube with a separator or dielectric between them. But in order for the electrodes to fit in our coin-type devices, we must punch them into discs. With a hammer and disc puncher, we will punch out these electrodes on a board with a sheet of plastic on top. For ease of use, I like to tape the plastic sheet to the board. We will also cover the foil with whey paper so as to preserve the integrity of the punched disc and prevent cross-contamination. We will examine the foil for an area that is homogeneous and smooth as can be, then align the disc puncher. With one solid hit from the mallet, we will punch out the disc. The electrode will be sandwiched by discs of plastic and whey paper and can be extracted with tweezers and placed into a small bag. It will be important to label these electrodes in the bags that they're contained in and not mix the anodes and cathodes, which may cause them to not work. When done well, a single recipe of slurry consisting of 80 milligrams of active material, 10 milligrams of carbon black, and another 10 milligrams of PVDF can make between 3 and 5 good electrodes. Up to this point, I've shown the preparation of the cathode. Making the anode follows the same procedure, but uses graphite rather than the NCM powder. If we wanted to make a supercapacitor, we would use activated carbon for supercapacitors as the active material in both the cathode and the anode. From this, we see that the properties and nature of the devices we make is heavily influenced by the type of active material used, as well as the ratio of materials in the electrodes. A material is considered activated or active if it has a highly porous morphology on a microscale level that drastically increases its surface area available for chemical reactions to take place. On the screen then, we can see the morphology of the graphite electrode under secondary electron imaging, as well as the nickel cobalt magnesium electrode, both having a highly porous surface that lends to how well they do in conducting electrons. Having now prepared both the NCM cathode and the graphite anode, we should now weigh them to determine how much active material is on the electrodes going into this battery. We can get this active material weight by determining the average weight of an aluminum or copper disc and then weighing the respective electrodes. Subtracting the weight of the disc from the electrode leaves the amount of total material, but we want the weight of the active material. However, we know that ideally the electrode contains approximately 80% active material out of the total, so we multiply the total amount by 0.8 to get the weight of the active material on the electrode. This information is important because we can use that to characterize the device. Knowing the weight of the material allows us to determine the capacity of an electrode, which varies by each material's specific capacity, or capacity per gram of material. Multiplying the weight of active material in the electrode with the specific capacity of that material provides the theoretical capacity of the electrode. This information is plugged into our testing software and provides us with the graphs that gives us the efficiency of our battery. For supercapacitors, we use the weight of the active material to get the specific capacitance, or capacitance per gram of material. Ideally, we want both our batteries and capacitors to have high efficiencies as well as high specific capacities and capacitances, respectively. In order to assemble our battery, we must transfer our components into a vacuum glove box. The glove box is moistureless and filled with argon, which makes for a non-reactive assembly environment. Before we put our electrodes in the chamber, we must evacuate and then purge that chamber 3 times. After the 3rd time, we may open the chamber and place our electrode. Note that I will make a point of opening the bags. If they are left closed, the positive pressure inside the glove box will make them nearly impossible to open. So by leaving those bags open, we allow the pressure inside of them to adjust to that of the glove box. Placing the electrodes inside the tray and locking the chamber, we will then evacuate and purge another 3 times. When purging with materials inside of the chamber, be sure to do so slowly, otherwise the electrodes will fly about inside the chamber and may cause damage to them. The assembly of these devices in the inert glove box is unique to our batteries. Note that supercapacitors may be assembled in the open air. With all our materials prepared, we will now begin the assembly. I will start with the small cap with an O-ring to serve as our base. Next, I will add in a steel spacer. Note that throughout the fabrication process, I'm using a plastic pair of tweezers to grip the components, and am assembling them on a plastic tray in order to prevent shorting out the device before it's been completed. I will now add in the graphite anode, attempting to center it as much as possible in the device. Next, I will take a separator that has been saturated with electrolyte and place it over the anode. It may be difficult to precisely center it, but still attempt to do so. Using the back of the tweezers can be helpful at times. Then I will add the NCM cathode, material side down so the material sides of both electrodes are facing each other and are in contact with the electrolyte-soaked separator. Once again, we will try to center it as much as possible, though primarily aiming to align it with the anode. We do this to maximize the surface area where reactions can occur on both sides of the battery. Continuing on, I also add in a second steel separator. Now, in order to ensure good contact within the device, which in turn ensures the device has a complete path for the flow of electricity, I add in a circular spring. At this point, the assembly is nearly complete. Adding on the large cap, I will then use the tweezers to flip the device and place it into the hydraulic crimping press. Making sure the knob is turned to the lock position, I then place the device into the notch and begin raising the platform. I will do this until the pressure on the gauge reads between 800 to 1000 psi, and then I will wait 10 seconds before unlocking the knob. Before the next use, I'll typically return the knob to the locked position. Using the tweezers to remove the sealed device, it is now finished and ready to be plugged into the current boxes for testing.